Okay, now we're going to talk about what are called inflection points. So I've written down the word here, point of inflection. Now this is really similar to a critical value from the first derivative test. If you remember, the critical value in the first derivative test is where is the derivative equal to 0 or where is it undefined. Those were critical values or critical numbers. This is really similar. In this case, we're thinking about the second derivative. Now, you might wonder, why do we need to study this? Well, think about it this way. If you didn't have a graphing calculator, knowing these things about the derivative, such as inflection point, would help you actually sketch the graph. And that's really the whole purpose of this. And you have to understand, when calculus was invented, they didn't have access to a graphing calculator. So they came up with different ways that would help them construct the graph. And one of those tools was this concept of inflection points. So an inflection point is a point in the second derivative of a function where either the derivative equals 0, the second derivative, I should say, equals 0, or the second derivative is undefined. It does not exist. And again, where would that be? Well, there might be a hole in the graph where it's not differentiable there, an asymptote, for example, as well, a cusp or a corner, and also a vertical tangent. So those are some cases. So consider that the concept of differentiability still comes into play. All right. Now, most importantly, though, for it to actually be an inflection point, the second derivative has to have changed sign across that number. So what I'm going to do is I'm going to show you two little wiggle graphs here. The first one shows a wiggle graph with -3 as an inflection point there, or not an inflection point, but kind of a critical value. But I want you to notice that it goes from positive to positive across this. So this one is said not to be an inflection point. But let's take a look at the number 5 in the second wiggle graph here, and we look at it, and well, it goes from negative to positive, and it does change sign, in fact. So this one indeed is an inflection point. Okay, so kind of keep that in mind when you're doing this kind of second derivative test, that you keep these things in mind, that it has to change sign in order for it to be an inflection point. Now, the other thing you might be wondering is, well, why do we need to know? Well, what is an inflection point? I'm going to give you a preview of what's coming. It's the point at which a function changes what's called concavity. So this one is said to be, if it's positive, concave up, concave up. If it's negative, concave down, concave up, in this case if it's positive. So what do we mean? Well, if you're drawing a graph that looks like this, and suppose maybe it's a sine or a cosine curve, all right, this point here, and I'm going to denote it in blue, if you notice, this is concave up and this is concave down. This point right here that I'm about to highlight in green, all right, is the inflection point, because that's the point at which the graph changes its concavity. Okay, so just something to keep in mind again for the future. But let's go ahead and take a look at a couple of examples. Okay, here is the first example. We're given y. I'm going to call it f of x just for the fun of it. Okay, so let's say this is f of x, and I want to find the first derivative, f prime of x. There's my prime. And what do I get? 3 times 4 over 3, that's 4x to the second power minus 2 times 12, 24x plus 10. The 45 derivative is 0. And now we take the derivative one more time, f double prime of x. All right, the 2 times 4 is 8x minus 24, derivative of 10 is 0. So now what we do with this is we set this 8x minus 24 equal to 0. So then 8x equals 24, and x ends up equaling 3. All right, so what we do is we construct our wiggle graph here, f double prime of x, with the number 3. And we're going to check, does the second derivative change sign across the number 3? Well, how would you do that? You have to pick numbers test points, if you will, to determine the sign. We really don't care what it produces, just we want to know if it's positive or negative. So you're going to plug a number in here for x, where it says 8x minus 24, your second derivative. That's why I always write f double prime. This tells me where do I plug in my number, my test point. So let's pick a number like 0, for example. That's before 3. 8 times 0 is 0, and you're left with negative 24. So that's negative. And then you pick a number after 3, suppose 4. 8 times 4, 32, minus 24 is positive 8. Again, we really don't care what it evaluates to. We just want to know the sign, positive or negative. Well, if you notice there, it actually goes from negative to positive. So this indeed is an inflection point. Okay, so I'm going to write that down here, that it is an inflection point. All right, there it is, inflection point at x equal, what is this, positive 3. So this, you could say is the answer, but they want in this particular question the coordinates of the inflection point. So we're going to just take it one step further and just go back to the original function, f of x, and we're going to plug in 3. So that's not a big deal. If you've got a calculator, I'm sure you probably already have the answer now. But I'm just going to model this, and then I'll just write out what the answer is. So that way you know what to do when you get to a problem that's very similar. Well, you plug in 3, and coincidentally, it spits out the number 3. So you have an inflection point indeed at the number, or I'm sorry, at the point 3, 3. So that right there is our answer for our first problem. Okay. Now we're going to take a look at this second question here, and let me move this up a little bit. Right about there is good. We're going to take a look at this next question here, and we're going to set it up very similarly. So again, I'm going to call this f of x. All right. And so I first find my first derivative. Again, we're not using the first derivative, but you could, because then you can discuss things like critical values and minimums and maximums and all that. So you might get a combination problem in your homework or something. So taking that first derivative wasn't futile. You need it to find the second derivative, but it's definitely helpful. So let's see, 4 times 1/2 is 2x to the third power. 3 times 2 is 6, so minus 6x squared. And the derivative of 12 is 0. And one more derivative here, the second derivative, 3 times 2 is 6x squared, minus 2 times 6 is 12, 12x. And it looks just like that. Okay, so now we set this equal to 0, but again, we do a little bit of factoring. We can factor out the greatest common factor, and we get something that looks like this. And this is really nice factoring, because then we just say, well, x equals 0 and x equals 2. All right. And now we can most certainly do our wiggle graph for f double prime of x. And we get something like this. Let's say we get 0 and we get the number 2. And we pick those quote unquote test points, before, in between, and after, and you plug it in here and here in the second derivative. All right, so you can pick numbers like -1, 1, and 3. Those would be good, but I'll leave you to that. You can pick out whatever it is that you want, but just verify with me. This is positive, negative, and positive. So these indeed are what we call inflection points. Okay, and it's important to note that on this wiggle graph we have negative infinity to infinity, because later on you're going to go on to talk about intervals of concavity, and that's another video for another time, and it's actually the next set of videos that we're working on here. But let's see, we could say we have inflection points at, because there's 2 of them, x equals 0 and 2. All right, 0 and 2. And so let's see here. I'm going to write inflection point points at, and actually I didn't evaluate. Silly me, I didn't do that. All right, we can do that right here below. All right, f of, let's see, 0 and f of 2. All right, that's what we need to do. We need to plug that into the original function. I'm jumping the gun here with my steps, but that's okay. I knew the answer already anyway. You get to the point where you could probably do this stuff in your head without a calculator. All right. Anyway, you plug in 0, you're going to get 12. That's pretty straightforward. That one was the easiest one. The plugging in the 2 is a little more challenging, but I mean, when you do the math, you get something simple, 4. So inflection points then can be found at 0, 12 and 2, 4. And that's where it happens. Those are the inflection points. All right. So not terribly difficult. This concept of the second derivative piggybacks right off of the first derivative and real similar to the first derivative test. But we're building up to this idea of concavity because then it helps us sketch graphs without a calculator. And that is really the concept behind all of what we're doing here. How can we operate and function, no pun intended, without a graphing calculator? Okay, so fairly simple, fairly straightforward. I hope this video was helpful, and as always, remember, like and subscribe.